So for some reason we tend to oppose science and religion, and we often say that Galileo is that symbol of the scientist who fought religion. But I think that this story is deeply flawed. First of all, because Galileo was an actual Catholic. So in fact, when he was young, Galileo wanted to become a priest. But then he turned into medicine. He registered to the University of Pisa for studies of medicine, but he didn't like it there. Part of the reason why he didn't like studying medicine is that he found out that the content of the courses that he was taught was completely controlled by the Jesuits, which were a religious group in Rome. So instead, Galileo learned how to draw and how to do mathematics. The drawing would be very useful when he would watch at the sky and through his telescope, because of course by that time you didn't have any smartphone or any camera to take pictures, so you had to draw what you saw, and it was very useful for Galileo to know how to draw. But obviously, the more important aspect of his learning is that of mathematics, because Galileo's key idea was to introduce mathematics to his endeavor of understanding the world around him. As an early example of Galileo's use of mathematics to understand the world around him, so according to legend, he was in a church and looking at a chandelier that was oscillating, and he measured the oscillation, the period of oscillation, which means the time that it takes for the chandelier to go back, forth and back. And this period, he measured it with his pulse, which is quite funny. Like these days, you would usually do the opposite around. You would measure the pulse using a clock or something like that. He found out that something quite amazing, actually, that the period of oscillation of a chandelier does not depend on the form of the chandelier, nor on its content or its matter, the matter it's made of, or it doesn't depend either on the amplitude of the oscillation. That one is not exactly true, but whatever. And actually, Galileo found out that the only thing that the period of oscillation depended on was the height of the cable you use to have it hanging from the roof. And Galileo even used mathematics to find this relation between the height, the length of the cable you're using, and the period of oscillation. He found out that the period of oscillation was proportional to the square of the length of the cable, which is quite surprising and amazing. Anyways, the bottom line is that Galileo was, from this point on, willing to use mathematics to really understand the world around him. And this is a very different approach from the approach that was used by the Jesuits, who were using old written works like the work of Aristotle to understand the world around them. And this would lead Aristotle to clash with the Jesuits. But of course, what he was really clashing against was the thoughts, these Aristotelian kind of thoughts that the Jesuits had. So really, Galileo's enemy is really Aristotle, I would say. Definitely not the church. In fact, he was a Catholic. So he had 3 children, 2 girls and a boy. And it is true that these are all illegitimate children, but it was not that weird at that time. Even some popes had illegitimate children, so he was not that anti-Catholic. And in fact, he sent his 2 daughters to the convent. So really, he was really Catholic. He remained a Catholic all along his life. And in fact, the future pope was a very good friend of his at that time, which will turn out to be very important later on. Now, Galileo's war against Aristotle did not start from out of nothing. It all came from the invention of the telescope. So Galileo found out that if you take 2 lenses and if you put them in exactly the right way, you could design a sort of glasses, like he called it a telescope, so that you could see very much further details that you would not be able to see with your own naked eye. And this was very useful for the army, for the military people, because you could use this to look at the horizon and look if enemies are coming from far away. So this made Galileo quite rich and very famous, but perhaps most importantly, it gave him a way to look at the heavens in a way that was not doable before him. And so he looked at many things. He looked at the moon. He saw that the moon was not a perfect sphere, as opposed to what Aristotle said. He instead saw valleys and mountains on the moons, which he calculated. But most importantly, he saw that the moon was not what Aristotle said it would be. But this was a first hint that Aristotle did not only say truths, and that there were good reasons to doubt whatever Aristotle said. Now, using this telescope, Galileo also found out amazing things. He found out that Jupiter had a sort of moon-like objects that were turning around Jupiter. So Jupiter had its own moons. He saw that Saturn had ears. Well, not actual ears. It actually has rings, but of course Galileo could not see in details those rings, so he thought that they were ears. And he also saw that Venus was lit in a certain way that implied that at some points Venus was further away than the Sun, but at other points it was closer than the Sun. And this really led him to the conclusion that perhaps the most important object in the solar system was not the Earth, but rather the Sun. And so when he read Copernicus, of course he was very charmed by the idea of putting the Sun at the center of the cosmos. Now, there are at least two other reasons why Galileo really started to doubt whatever Aristotle had said. The first of these reasons is the law of falling objects, and it's really an amazing story. Well, first of all, Galileo made a lot of experiments to sort of suggest the fact that Aristotle's law of falling objects was not quite accurate. Just to recall, Aristotle's law of falling objects says that heavy objects fall faster. Now, that's something that's quite true in practice. If you actually go up to the Pisa Tower or the Eiffel Tower or the Empire State Building and you throw two objects of different weights, then usually the heavy object will fall faster because of air friction. So Aristotle's principle of falling object was definitely consistent with the observations. But the genius of Galileo was to show that Aristotle's principle, when you try to really push it, to really find out what it says about different settings, then you find out that at some points it can make one prediction and the opposite prediction as well. The theory is self-contradictory, it is inconsistent. And this shows that Aristotle's theory cannot be right, it has to be wrong. And so he had here a mathematical proof that Aristotle did say some pretty wrong things. Now, there's another principle that Galileo put forward and that contradicted Aristotle, which is the principle of relativity. So according to the principle of relativity, if you're on the top of a boat, of a ship, and you're throwing a ball, you're letting a ball fall, then the ball should fall at the bottom, just near, right on the vertical of the boat. Even if the boat is moving, the ball is falling with the boat, and in particular, the ball eventually will be moving with the boat. The ball will not come to a rest. And this was in contradiction with the idea of Aristotle that all objects tended to be in a natural state, and the natural state of objects was not to move. Instead, Galileo said that that is not the case. Actually, objects tend to move, and the natural state of motion is to keep their motion going on. What slows down the objects from our frame of reference, from the frame of reference of the Earth, of the ground of the Earth, is air friction or like all the frictions, all these things that make the theory not perfect. Now, what Galileo is saying here is really amazing. I think it's one of the greatest insights in the history of epistemology, the science, the philosophy of science. He assumed, he made this amazing bet that if you wanted to understand the real world, you should forget about the real world. You should come up with theories, laws, and principles that were extremely elegant, mathematically very beautiful, and that sort of forgot about some of the perturbations, some of the the bad, ugly stuff that do occur in the real world, like air friction. And when you do that, you can reason in an abstract world that doesn't really exist in reality. I mean, in reality, the principle of relativity is almost never verified. You cannot, there are hardly any experiments that you can actually do, because there always are going to be air frictions and stuff like that that perturb the experiments you're trying to set up. But Galileo's key insight, it was to imagine, or a rather crazy bet, was to imagine that if you wanted to understand the real world, what you should do is to come up with a theory or law in the ideal world of ideas, in the Platonician world of ideas, where everything could work out perfectly. And then from this abstract, unreal world that forgets a lot of things of the real world, and that is definitely not what's happening in reality, you could still use these to better have an insight, better understand what's going on in reality. That's a crazy bet. You're not trying to stick to reality. You're trying to move away from reality to better understand reality. This is really Galileo's crazy bet. And it's the bet of mathematical physics, or theoretical physics as we call it today, that this attempt to understand the real world with some very basic idealized mathematical universe that sort of forgets a lot about the real and fuzzy and difficult and complicated real world, but somehow better explains this real world than any other attempts that would try to stick to reality. If you're trying too much to stick with reality, Galileo is saying, you're not going to be able to really understand reality. That's crazy. But that's what we are doing today in physics. And what I like a lot about this idea is that it's a very Platonician idea. And Plato was Aristotle's master. So he's using Aristotle's master to contradict Aristotle, which I think is pretty cool. Galileo is often said to be the father of the scientific method. Well, I don't think he is. At least not the scientific method as we call it today. He did invent the idea of experiments, of controlling exactly what you're trying to do, trying to get rid of all the things that are going to mess up the ideal theory or hypothesis you're trying to test. He did come up with that, but the scientific method, as we teach today, which means that you come up with a hypothesis, you do experiments, and if the experiments contradict the theory, you just reject the hypothesis. This is not Galileo's. I don't think that you can say that Galileo thought along these terms. In fact, a great example of that is the example of how he tried to explain the tides. So you have to remember that back then, there was no theory of gravity. And the idea that the moon was acting on the earth was kind of crazy. At least to Aristotle. It was not crazy for the astrologists back then. But for Galileo was trying to come up with an actual mechanism. And he didn't think that the moon could be the cause of the tides. So instead, he tried to explain the tides using the fact that the earth is moving around the sun. However, this theory that he came up with predicted that every day there would be only one high tide. Yet, as everyone knew back then, there were actually two high tides every day. So Galileo's theory was contradicted by experiment, but he still pushed it forward, and he still he said that he had proved that the sun was the center of the universe, because this explained the tides. Which it doesn't, because it only predicts one tide every day. But Galileo was saying that, okay, there's two tides, but there's one main tide. And the other tide, it's something fuzzy, like something due to some phenomena, like some minor phenomena that occur on Earth that took the time to really explain. Just like he didn't really take the time to explain the reason why heavy objects do fall faster in practice. It's just like, in reality, there are things that are messing up with the theory. But the big ideas, but there are some big idealized versions of this reality that allow to better understand what's going on in reality. That's Galileo's amazing, crazy bet. It worked very well for the falling of objects and for the principle of relativity. However, for the explanation of tide, it did not work at all. Today we know that this theory does not work. What I'm trying to do here is to justify the reason why, at least according to Galileo, the fact that his theory of tides was contradicted by observation was not that big a deal. He still believed in his theory even though it was contradicted by experiment. That was also the case with his other principles. And having said that, I think it's pretty clear here why it's hard for me to say at least, that Galileo is the father of the scientific method. He's not. And so he was very arrogant, and this gave him a lot of confidence, at least, to claim that heliocentrism, that a sun-centered universe, was the right theory, was the right way to do it, was a fact. But if you look at the evidence back then, it's clearly not that obvious that the world was sun-centered. So for instance, the Copernican system that put the sun at the center was not actually sun-centered, because planets were orbiting around a point that was next to the sun, but that was not the sun. So it was not that much of a sun-centered system. The sun was very close to the center of the universe. So like graphically, when you represent it, it looks quite nice. But if you look at the details of the Copernican system, it's anything but simple. It's a very, very messy and complicated theory. In addition, there was an argument that was put forward by Archimedes 2000 years before, but that was put again forward by Tycho Brahe, who had a very in-depth study of a lot of things in astronomy. And in particular, what he studied is the so-called stellar parallax, which means that basically between December and June, between two opposite months of the year, your position in the universe should be different, and therefore you should see the universe in a different way. In particular, certain stars should be displaced. But Tycho Brahe made very detailed measurements and found out that there were no such deviations, at least no observable deviations of the positions of the stars between every 6 months. And so this really showed, and this really suggested, that the Earth was actually at the center of the universe, and that we always see the star in the same manner because we're not moving with respect to the stars. And this was a really brilliant idea. I mean, it was and this was actually the argument used by the Inquisitions to punish Galileo eventually. So and I really want to stress the fact that it's a very sound argument. Now, the reason why Tycho Brahe was not able to detect any deviation is, first of all, because his measurement devices were not good enough, and second, because people could not imagine back then that the universe was as big as it is and that the stars were that far. They assumed that the stars were not that far, and therefore you could see this deviation in their position. If the stars are really, really, really far, then there's no deviation. Nevertheless, Galileo was perfectly convinced by heliocentrism, the idea that the sun is at the center of the universe. And you might argue that part of the reason why he thought that is that it was the opposite of Aristotle's theory. He just wanted to contradict Aristotle. There were definitely more than just this will to contradict Aristotle, but I cannot imagine that he did not play a part in his chain of thoughts, because he was really fighting Aristotle all along his life. He was fighting against Aristotle and those that believe in Aristotle. So proving them wrong was probably very seducing for Galileo. So Galileo actually asked for the authorization by the Pope to write a book about this debate between heliocentrism and geocentrism. And the Pope agreed, but the Pope asked him to be very neutral and to really stress the fact that heliocentrism was a theory, was not a fact. And I think it's a very sound argument. Like, I don't think you can really blame the Pope for having said that. Now, the thing is that that's not what Galileo did. So in his book, he enacted two characters. One was a heliocentric person, like kind of like Galileo or Copernicus, and the other one was a geocentric guy who was kind of representing Aristotle, but as well the church, the Pope, and everyone, and all the Jesuits. And the name he gave to that guy was Simplicio, which basically means stupid or naive. And all along the book, this guy really seemed stupid, naive, and that's and so if you read through the lines, and you don't really need to give it a lot of try to read through the lines, you can imagine that through this book, Galileo was actually mocking not only Aristotle but as well the Pope. And of course, if you're mocking the Pope in a public book that the Pope authorized before it was written, of course you're going to get into trouble. It's a matter of egos, it's a matter of power. Galileo upset a lot of very powerful guys. Of course he was going to get punished. And he did get punished. So he was sentenced to stay at his home for the rest of his life. Which, when you think about it, is not that bad for what he did, I would say. And again, I would say that the arguments of the Inquisition were very sound arguments, were like what we would call scientific argument today. So what I've hoped to show you through this storytelling of the life of Galileo is that religion did not play a big part in this story. It really was more of a story of power, of conflicts of power, of authority. And Galileo upset a lot of very powerful people and got punished for that. And I'm saying this because I think there may be something equivalent going on these days, where some topics, like typically religion, are being put forward where in cases where they have no role to play, where they don't actually have any role to play, like for instance when we're talking about terrorism,